I'm Flaviu Cipcigan, and I am a research staff member in impact science at IBM Research. We tackle some of the most complicated problems using some of our more advanced technologies, supercomputing, artificial intelligence, quantum computing, and we are all applying that to solve some of the most challenging problems, such as discovering new materials for climate change, such as being able to discover new medicine. So my background is as a physicist. As a computational physicist, I use computers to understand nature. I did my PhD in physics at the University of Edinburgh, developed some new techniques in order to simulate matter, atoms and molecules. And now I came to IBM to apply some of those techniques. I applied them to problems in healthcare, discovering new antimicrobial peptides, and I'm now applying them to solving some of the biggest issues we have, such as tackling climate change. So supercomputers were always driven by the idea of trying to see how much performance we can get out of computers. And there are some problems which need this kind of performance. For example, weather modeling. Weather modeling or climate modeling, right? To be able to predict how the Earth is going to change as we say emit more carbon dioxide, we need a lot of computational power. And so this is one of the reasons we build computers that allow us to harness this computational power in order to solve really hard and complex problems. And so this is for me. I think there are multiple drivers, right? But for me, I think what's really important is this driver in building new, better supercomputers, which are more powerful, so we can tackle some of these more challenging problems. Actually, I was talking to someone, and in a sense, the more powerful of a computer you have, the more in the future you can be, right? Because now, in our pockets, we already have a supercomputer in our pockets. It's just that what's in our pockets now in our phones used to be a supercomputer in those bunkers that you said, or not in those bunkers, but like in these big data centers, used to be a supercomputer 20 years ago. I actually so on my phone, I ran one of these performance benchmarks. They call it LIMPAC, right? It's used to figure out how powerful a computer is. It's how supercomputers are being ranked. They are being ranked by running these benchmarks to see which is the best, which is the fastest supercomputer. For example, for IBM, we built some of the fastest supercomputers, Summit and Sierra, in the world. And so we test these things to see where they are. We compiled these lists, top 500. I ran this on my phone as well, and I looked at like when my phone was a supercomputer, and it was like about the 1990s. So yeah, it gives us access a little bit, but it both gives us access to the future, so that's one thing, and the second thing is that it allows us to tackle some of the problems we need now, but we don't have like the power to do now. Drug discovery, being able to, so we at IBM have launched the HPC consortium, High Performance Computing Consortium, which brought together all of the big supercomputing centers in order to tackle the COVID-19 pandemic. And this is kind of like the sentiment that we all had during the pandemic. This is such an unprecedented circumstance. We all need to come together in order to solve it. We pulled in that computational power and used it to help people run simulations and build models in order to understand a new disease. So it's supercomputers, it's artificial intelligence, all of these techniques that allow us to accelerate discovery, to do science faster. Say in the lab, I can work with some of the most talented lab chemists that I know. I work with them in IBM Research, and they can do maybe 5 experiments a week. They can do maybe 10 experiments a week. They can build autonomous labs, and they may be able to do 100,000 experiments a week. But if you manage to build a computer model so that allows you to replicate some of the experiments in code, that maybe allows you to do 1 million experiments a week. So you can test out hypotheses faster. You can test out your ideas faster. Because this is kind of like the whole process of doing science. You start with a question in mind, or you start with an area of investigation in mind, right? I want to discover new materials to capture carbon. And then you ask questions. What is already known? You can ask questions to other scientists. You can ask questions to the body of knowledge, and we can use artificial intelligence to build a representation, and build a system that allows us to answer that questions from that body of knowledge. So you ask other scientists, you ask the body of knowledge. Maybe you ask nature. You build simulations of what nature can do. You test out those simulations. You're like, all right, these are good. These are a good representation of nature. Then you can ask those simulations. And all of those things allows you to answer questions so that you can eventually get to the breakthroughs that you need in order to solve some of these great issues, such as climate change. Well, a lot of the supercomputers in this world are now accessible through the cloud. Like I can go on my laptop and just type in a few words, and I can get access to some of the biggest supercomputers in the world. This is like the power of the cloud. I don't need to have the supercomputer in my backyard. It would be very hard to do that. But I don't need to have the supercomputer in my backyard, right? I can go, I can type in a few things, and I can access a supercomputer. I can build my own mini supercomputer, right? The cloud gives us access to platforms, gives us access to building blocks that we can use to say like, hey, I need this computer to solve this problem. I need this amount of computational power, 8 nodes, 10 nodes, etc. So I'm like, how much computational power do I need to solve this problem? I'm like, okay, this much. I go, I'm like, okay, I type in, and I like, give me this amount of computing power. And almost instantly, very quickly, I get that computing power. If I have the money, like I have a certain cost. But it's cheaper than actually going and building this giant machine. Maybe I need the giant machine. Then I can, sort of using more money, I can build that giant machine on demand in the cloud. So that's one of the directions that we are moving in, like on-demand compute power in our hybrid cloud, in IBM hybrid cloud. Or we have these giant machines which take a long time to build, but they are used for really heavy lifting. They're used for climate predictions. They're used for some of the most challenging simulations that we need in order to discover new drugs. There are data centers somewhere in the world. One of the things actually that, so if we talk about supercomputers, the traditional supercomputers, which are not, they kind of are accessible, and that's, I'm trying to sort of think how to explain this, but let's go traditional supercomputers. Big machine is sitting somewhere. One of the really good things about that big machine is it's very interconnected, right? Bits of one machine, or parts of one machine, can communicate really fast to other parts of that machine. We call this the MPI, Message Passaging Interface Protocol. And so those parts allow, so one part of a supercomputer can pass messages quickly to another part of the supercomputer, which allows them to do computation. That is what we call parallelizable. It allows us to take a computation, split it over multiple computers, right? I can't fit that computation into a single computer, into my laptop. So I need to split it over multiple of these laptops, not laptops, but of these computers. And so I did that computation, I split it, but if I split that computation, eventually those nodes have to talk to each other. So I do a little bit of computing here, do a little bit of computing there, then the nodes talk to one another, they get to an agreement, and then the computation can continue. It's kind of similar to how people collaborate, right? You do your own thing, then another person does their own thing, then you get together in the meeting, you discuss this thing, and then you move forward, right? So you've got supercomputers which can talk to each other. You've got the individual computers that can talk to each other really fast. So that's one of the great things about supercomputers. Lots of compute power, really, really powerful computers that can talk to one another fast. So that's the purpose-built ones. And there's also the cloud ones, which are more flexible. And we are working now. Some of my colleagues, it's not the area that I'm specifically focused on, but some of my colleagues are working on making these cloud computers communicate as fast as the large purpose-built machines. But this I would see as not a parallel, but kind of the spectrum of, and they're all really useful, like the machines that can communicate really fast and the machines that are accessible through the cloud. So at IBM Research, I work in this initiative called Future of Climate. There we are building technologies to mitigate the effects of climate change and to adapt to the changing climate. One of the problems that I work on specifically myself is materials discovery. We plan to discover new materials to mitigate climate change, specifically to capture carbon. There's still a lot of carbon-emitting infrastructure being built, power plants and such. And so if we want to get to net zero as fast as we want to get to net zero, we have to get to net zero really fast, we need to start capturing some of that carbon from those power plants. And that needs materials innovation. That needs new molecules, new, I also call them sponges for CO2, new materials that can capture that CO2 out of those power plants. So we are applying these technologies to discover these new materials. It's really interesting because, like, in the field that I am working on, so the specific problems that I am working on right now, but that doesn't mean the field itself doesn't need more power, but the specific problems that I am working on right now, the idea, what's more important is the masterful use of the compute power that we have rather than needing more compute power. But I think that depends very much about the scientific challenges. And I say masterful use, right? I say that because of two things. First one is that, say we have artificial intelligence models, right? We need GPUs in order to train those artificial intelligence models. But we also need good data to train them. We need good algorithms that can make sense out of that data. So raw compute power isn't everything. It's an important part, and sometimes can be the limiting factor. It's good to know that it's there and you can expand it. But it depends on the problem. Sometimes the limiting factor can be, do we have enough data? Sometimes the limiting factor is, do you have algorithms which are good enough in order to make sense out of that data? So we have groups who work on algorithmic innovation, who are like, let's build more algorithms, better algorithms to make sense out of that data. There are groups in sort of the material design field that I work in that look at generating data. Can we run experiments that do this, this, and that, and generate quality data? There are groups who work on how do we harness the compute power? How do we build better architectures on top of OpenShift to harness some of the compute power, or harness some of the compute power of the big supercomputers? And so all of these work together in order to solve our challenges. The people who build faster, bigger, better supercomputers, they give us the raw material, they give us the raw power. Then you got people who build really interesting techniques, good algorithms on that raw power. There are material scientists, experimentalists, who give us some of the data that allows us to use that raw power in service of nature. And all this thing comes together in order to fuel innovation. And we got, like, for example, IBM has recently released its 2-nanometer process. So we are continuing to build better, faster supercomputers. Actually, my colleague Tamar, she can talk much better about some of the evolution of supercomputing. I think she has talked in her interview about the evolution of supercomputing and of computing in general, and how to make that more sustainable, because she is the one who is working deeply on that. My expertise is very much using these tools in the service of science. This is such an interesting problem. I think the limit is, or maybe not the limit, because I tend to see this quite optimistically. It's where there's scope for innovation, right? A lot of the places where there's scope for innovation is putting together things, building solutions, building tools out of the building blocks that are given to us by the computing innovation. One building block is compute power, right? You can access that to the cloud. I can access one supercomputer. So you take that, that's one building block. You've got artificial intelligence models, that's another building block. You have data, that is another building block. And making sure that all of those things fit together nicely in the service of the problem, that in itself is a challenge. And as you move fast in that challenge, then you maybe realize, well, you need algorithmic innovation here. So you do a little bit of algorithmic innovation. You might say that, hey, I actually need more compute power. So you go and find more compute power, and then you move forward. I'll give a very specific example. So I worked on accelerating discovery of antimicrobial peptides, short proteins that kill bacteria. In that project, we needed both algorithmic innovation, so new algorithms to make sense out of the data that we had. So data was limited, okay. Algorithmic innovation to make sense out of the data, and then innovation to put the things together. So being able to communicate between people who have decades of expertise in the lab and people who have lots of expertise in artificial intelligence, and being able to put that together in order to build a system and build the result that gives you in the end, that gives you new insight. So I know this was a little bit of a long answer to this, but this is the perspective that I have right now in how we solve these problems. At IBM Research, we recently released the quantum roadmap. Again, my colleagues are working on this, but I eagerly await some of their results, because what it gives me, or what it gives us as well, is the power to use nature to simulate nature. So quantum mechanics, I'll start a little bit of why I'm excited about quantum computers, and then I'll talk about some of the applications that I see coming. So why I'm excited about quantum computing, right? Using nature to simulate nature. Molecules, atoms and molecules, they operate using the laws of quantum mechanics, or by the laws of quantum mechanics. Us here have different sets of fundamental laws that allows us to kind of predict what we do, classical mechanics. And quantum mechanics and classical mechanics are very different. Current computers operate a lot on the laws of classical mechanics, classical information theory. Quantum computers operate on the laws of quantum mechanics. And so, if you build something that operates on the laws of quantum mechanics, it allows you to better, faster solve problems which are quantum mechanical in nature. We want to discover new molecules to capture carbon out of the atmosphere, right? So those molecules operate by the laws of quantum mechanics. So it's really good to use a quantum computer in order to simulate their properties in order to calculate what they do. And so you can answer these questions, such as how much CO2 this molecule absorbs. You can answer these questions faster than you would be able to do with the classical computer. So this is one of the things that's really, really exciting about quantum computers, is that it allows you to simulate nature using the laws of nature. And so once this technology is built, and once, like, we are building this really fast, but once the technology gets to the point of being able to, and actually we can do some problems now. So it's kind of this thing of what problems we can do with the quantum computers now, and then what problems we'll be able to do in the future. And once we can solve problems with quantum computers that allows us to model the molecules that we are interested in the field of carbon capture, then it's going to be really fun, because then you can really accelerate discovery. Okay, so let's start with the fundamentals, right? Climate change is an emergency, and we need to decarbonize as fast as possible. All around the world, we need to reduce the amount of carbon dioxide, methane, and other greenhouse gases that go into the atmosphere in order to limit warming to 1.5 or 2 degrees Celsius. We have agreed to do so in the Paris Agreement. We have internationally agreed to do so in the Paris Agreement. So we are, as a world, working towards a certain target. And one of my fundamental beliefs, and also I think, not just beliefs, but this is the thing we have to do as a world, right? We have to decarbonize. And the question is, how do we do this? And I think the key word to it is collaboration. None of us individually has the answer. One thing that I used to say a lot to my teams and to other people, we either win this together or we all lose this together, right? This is not a competition. This is a collaboration towards building a better future. And I have good friends who are activists. I have good friends who are scientists. And it's really beautiful to get together with them and listen to their worries, listen to the tools, listen to the things they can do well, listen to their voices. I work with this organization called Global Shapers, Manchester. I co-founded Global Shapers Manchester. This is a community of young people who want to have impact in the world. We are 19 of us right now. We get together and do small local projects in our local communities in order to move towards a better world. It's a volunteering thing. We are part of the wider Global Shapers community, a network of over 10,000 young people who are committed to build a better world. And we are all like, I see projects that are happening all over the world, and I'm fascinated by the ingenuity of people. Again, not the things that I do myself, but some of the things that people have done is, there's a big campaign to plant 1 trillion trees, trillion with the T, around the world in order to suck some of the carbon out of the air, not chemical absorption. So I work on discovering new materials to capture carbon out of the air. I know people who work on planting trees to capture carbon out of the air. We've got so many tools at our disposal and so many tools that we can build. So innovation gives us more tools. And we have some of the tools right now. It's, let's go. Let's do some of these things. So yeah, I think this has been a very complex answer because it is a very complex problem, right? There is no, like, this is the one sliver solution that everyone does. It's a problem that we have to come together. We have to understand it from our multiple angles, and then, yeah, move forward towards solving it. The International Energy Agency released a table that looked at the maturity level, like how far advanced certain technologies are, and only a few technologies are at the level that you can go and install them on a power plant right now. Hence, there is need for innovation because we don't have enough technologies, and the technologies that we have are not yet good enough in order to start capturing CO2. So yeah, we need innovation. Why am I passionate about climate change? It's one of the biggest issues that we need to tackle now as a society. And as a scientist, right, I want to use my skills for good. And this is one of the biggest things now that needs innovation. And so I'm working to use those skills in order to supply that innovation.